Hello, my name is Jose Esparza. I'm a student at the Massachusetts Institute of Technology. I'm part of the experimental study group, and today I will be talking about the connection between electricity and magnetism. You probably experience electricity through your daily life with batteries or with your cell phones, computers, whatever. You've probably also experienced magnetism when it comes to playing with magnets or hearing about the poles of the Earth and of other planets. Well, today we will be connecting why these two phenomena are exactly the same force and exactly the same thing through the use of special relativity. Now, electricity and magnetism were connected way before special relativity by the work of many physicists, particularly Faraday and James Maxwell. Now, but it turns out that special relativity gives a very clear explanation as to why they are the same phenomena. Caveats of this video would be that we will be working on CGS units, centimeters, grams, and seconds units. And these are actually different from SI units because we use the SU instead of the coulomb as our unit of charge. So it makes many of the calculations different. We don't use the permittivity of space or the permeability. This is an example of Maxwell's equations. As you can see, they don't have any type of constant such as mu, epsilon. The divergence of E will be 4 pi rho. The curl of E will be 1 over the square root of negative 1 over the square root of speed of light. 1 over the speed of light, dB dt, and so on. So it makes it's a different type of units, and it makes our calculations better. The other thing is that you should be aware of is the transformations of special relativity. There's other videos that detail way better the way to transform frames. Just some examples, I'll be talking about length contraction and how to transfer forces. Lengths that move parallel with a motion near the speed of light will contract as 1 over, so if this was the original length, this new length will be the square root of 1 over the minus velocity of this squared over c squared times the original length, so it's going to be shorter. And for forces, but however, for perpendicular lengths, there will be no difference, which is important. For forces, perpendicular forces will actually have a difference of gamma, which is this constant here. The one here, this is 1 over gamma. So the force will increase, perpendicular forces will increase under these transformations if you're moving near to the speed of light. And but when you're moving force parallel with the velocity, then the force will actually not change. What I mean by different frames of reference, hope you're aware with special relativity, there's excellent videos about that. But just saying the lab frame means that we're observing a wire, or we're observing something, like as an outsiders, we're seeing everything as it happens. And the rest frame, we're putting us in a position as, for example, as a particle, as a spaceship that's moving. So on the rest frame, it seems like something that we're dealing with, for example, with this block. We would feel as if we were in the block and we were not moving, so there wouldn't be any velocity around us. But everything, there wouldn't be any. We wouldn't have any velocity, but everything around us would have a different velocity, probably depending on the transformation we use. And those sort of things that we're gonna need in order to show how electricity and magnetism are the same thing. To see the relationship between electricity and magnetism, let us analyze a typical wire from 2 points of view. First, as an outsider's point of view, as if we were looking at this neutral piece of wire with negative charges moving to the right on our coordinate system. And then we will look at this wire from the point of view of a particle within here. Let's say we have a particle here that has a positive charge Q, and it's moving at a velocity v to the right. We will have a neutral wire that has positive charges with a linear density of sigma, and it will have negative charges with a density of negative sigma for a total of a neutral wire. The positive charges will be fixed, and the negative charges will be moving at the right direction, which will yield a current at the left direction because these are negative charges. Why are the negative charges moving? Well, that is more consistent with our models of typical wires moving, in which the protons and the positive charges are fixed, and the negative charges, the electrons, are the ones that are being moved. Now, if we have this typical problem of a wire with certain current I, Then we can calculate what's going to be the force experienced by this particle moving at a velocity v. Using Ampere's law, we can see that we can calculate that there will be a magnetic field experienced by this particle because of these moving charges, and that this magnetic field will be equal to 2 the current times the distance between the wire here. Let's call this distance r over the speed of light. Why the speed of light? We're using CG as units, so hopefully that doesn't cause any confusion. Now, this will be equal to 2 times the velocity of our electrons times our linear charge density. Okay, and this magnetic force will be pointing at the y direction. Okay, then what will be the force experienced by this particle? Well, using the force, the Lorentz force in CG as units, we will get that the force experienced by a particle will be Q times the velocity of the particle crossed with the B field over the speed of light. What this will yield us at the end, is gonna be a force experienced by this particle of Q times V times U times lambda over RC squared, and this force will be pointing at the negative C direction. So the particle will be trying to move down. Okay, this is one point of view of what's happening. Now let's get us in the point of view of this particle. We will look at this from the lab frame, that is the point of view of this particle. Now, this particle used to be moving at a velocity v. Now we're going to look at it from the rest frame, and we're going to assume that this particle is at rest. We're going to assume that we are kind of like in the same position as this particle, and that this particle doesn't feel as it's moving. It just feels like everything around it is moving. Now, if this particle is moving at a velocity v, we have to transform everything to move to the v frame, to a negative v direction. So these positive charges that were not moving will now seem to be moving from the point of view of this particle as from the negative v direction. And these charges which were previously moving to the right with a u velocity will now move up from a velocity which combines u and minus v. Now, using Galilean transformations, we would convert it as our new u in our new frame, u prime, as u minus v. However, we're now using special relativity, and this transformation is not valid. We're going to use similar. We're going to use a Lorentz transformation, in which we have to normalize this by a factor of gamma, which would be, well, kind of gamma. Now this will be the correct velocity towards what this u is going to move. So it's going to move at a u prime velocity. Okay. So now we're thinking, okay, I guess they're different velocities. Does that make anything different? And the truth is that yes, it does make things different, because we assumed that this wire was neutral, that there was the same number of positive charges and negative charges. But now, because they're moving at different velocities, and we're saying that it's not the particle that's moving, but it's actually the wire that's moving, and the wire is not only it's all the wires moving now. Then there will be a length contraction of the wire. This contraction will be different for the particles that are. This contraction is going to be different from the positive particles to the negative particles. The reason why is that their charge density is going to change differently. Now, whereas the previous charge density for the positive particles was just lambda, which we denote as positive lambda. Now, which was the charge over the length. Now, since charge doesn't change with speed, this will become q over the new length. Whereas we know from just any regular length contraction that a new length, L prime, is equal to 1 over gamma the own length. So this is gonna be what's gonna happen. And this means that the new charge density at rest will be this gamma. Sorry, the new charge density at rest would be lambda times gamma. Okay, so we're gonna have a different charge density, and this gamma, by the way, this is gonna be gamma v for the positive ones. We're gonna define it as 1 over the square root of 1 minus the velocity of the particles over the speed of light. Cool. Now, let's see what's going to happen for the negative particles. Well, they're going to have now a lambda of q over L, which is going to be q over 1 over lambda L prime, which is going to imply that the charge density for the negative particles is going to be negative lambda gamma u prime, because they're moving at the u prime direction, velocity. Now this u prime, it turns out to be quite complicated, because gamma u prime is equal to 1 over 1 minus u prime over c squared. And as we can see, this u prime is actually pretty complicated. We can do some it's gonna take some algebraic manipulations, but afterwards we can figure out that this gamma, or that this whole equation, well, we can figure out after doing some algebraic calculations that is gonna be equal to gamma u 1 minus u c v squared. Okay. So now we have this. And now we can find out what is going to be the net charge on the wire. Well, the net charge on the wire, it used to be that the net charge on the lap frame, the net charge density, was positive lambda minus negative lambda, which was 0. But now our net charge density, as felt by different particles, will be lambda gamma v minus, there should be a minus sign here, minus gamma v 1 minus uv c squared. So we're gonna get this. So we're gonna delete the first term, and we're gonna end up with this. So we can see that now, whereas we used to have zero net charge, now we're going to have a positive net charge on the wire. So whereas this wire used to be neutral, on the point of view of this particle, this wire has an E field. Okay, so now that we have the charge, we can calculate the E field of this, just like if it were any regular E field, using Gauss's law. Now let's use Gauss' law for this. We're going to find out that if we just use Gauss' law, that the flux of the E field over the area of our Gaussian surface, and let's say our Gaussian surface is going to be just like something that encloses the particle, a cylinder, something nice, that this is going to be equal to um, 4 pi lambda times the length of our cylinder, which this is going to be 2 pi, let's say it's going to be distance r, so then we can cancel these. So then we're going to have a net E field. Then we can cancel the pi's, we can cancel the 2's. We can cancel the L's. I have this L here, so we can just cancel these ones. Move the R to the bottom. And we're going to get that we're going to have a net E field for this wire. That's going to be 2 times our charge density there, which is going to be gamma lambda u v c squared. Cool. So then this is gonna the charge here is gonna experience a force of in the r direction, just saying that just away from this. So in this case z. Then this particle will experience a force which is going to be q times 2 lambda v gamma v lambda naught u v down over r c squared. Now, hopefully this is familiar to you. I erased it, but hopefully this is familiar to you. The E field we got previously from the lab frame, erasing all this. Using our other frame of reference, using our first frame of reference, we got that there was a force on this particle. On this particle, there was a force F that was equal to 2q lambda uv over rc squared. And this force was pointing down. So that was our original force. Now we have this new force that is the same thing, except for this factor of gamma. So why are they different? Well, as we discussed earlier, under a different reference frame, we're going to have that this force is going to be, the prime force is going to be the same as the original force times a factor of gamma. Now, this makes complete sense with our the special relativity we covered in the beginning, but we have to think about what's going on here. This force, which we first saw on the lab frame when we assumed that this was a neutral wire, was produced by a magnetic field. This force here, however, is produced by an electric field. The forces are equal. The only difference of the gamma has to do with the transformation. But let's think of, so the magnitude is not the worry. What should worry us is, why are these forces so similar? We used to have a magnetic force, and we used to have an electric force. Well, that's what explains that the electric force and the magnetic force is the same thing. An electric force and the magnetic force are the same phenomena occurring at a different frame, at a different perception. This particle, we'll see that the particle itself is not moving, so it can therefore not experience a magnetic field, because you need a velocity for that. However, if I see the particle moving and I see this wire stationary, I will think that whatever's acting on this particle must be a magnetic field. The particle will feel, no, you're wrong, it's going to be an E field. And I'm going to be like, no, you're wrong, it's a magnetic field. And that's the beautiful thing about relativity, that nobody's wrong. What happened is that it is experiencing what we think is different, but it's actually the same force and it's the same phenomenon. And this is the beautiful connection of how special relativity connects the same effects of electric field and the magnetic field. As you can see by this result, they're the same thing. They just have the factor of gamma, which is necessary for any force transformation. And this just shows an example of how these two relate really well and really beautifully. Just giving another last note on unification of forces. This unification of electromagnetism and of electric force and magnetic force occurred in the 19th century and all that. And in this century, the last century, 20th century, we actually discovered, we humans, that the electromagnetic force is the same thing as another force we call the weak force. And we can assume that at some point in the universe, at very high energies, probably all forces were a unified force. And this is just an example of how two very different forces can be the same thing when viewed in a very specific manner. Thank you for your attention, and hopefully this will help you for your 802 or 8022 class.